All right, so, ladies and gents, everything that we've dealt with so far has been very nice in terms of it's on the x-axis, it's on the y-axis. Life is great, right? But that is not life. Like, amazingly, there are things in our world that are on hills, right? That are slanted, right? These things called ramps kind of get in our way, and they change physics and how we know. So we need to know how to do them, right? And they're not hard. They're exactly what we know already. We just need to adjust our point of view, okay? I will warn you right now that the way I'm going to draw things, while correct, may be a little bit exaggerated.
Out of scale?
Right? Out of scale. That's an even better way to say it. Yes, they will be out of scale just to make seeing things a little bit better, a little easier, okay? So here I've got this box. And let's just imagine that the box is hanging out. We're not going to worry about friction or anything like that. Amazingly, somehow, the box is just sitting on that ramp. It's not sliding. We're good to go. All right? So let's draw a free body diagram for it. Okay? So first thing, our convention, even though it's on a ramp, our convention does not change. So weight is still always going to go straight down. Okay? The normal force is still always going to be perpendicular to the surface. Okay? And that's it. Done. That's our free body diagram. We're not going to worry about if a string is pulling it or if a hand is holding it there or there's friction. Just for the sake of what we're doing, we're going to leave it like that. Okay? Awesome. Previously, or up until this point, we're drawing a free body diagram, right? Our free body diagram would look like this. Right? That would be our free body diagram. That's cool. That's perfectly acceptable. Okay? And if we needed to figure things out, we would have the y component of the normal force, and we would have the x component of the normal force. Right? Slight problem is that I really don't know what this angle is. Right? It's not apparent right away. Okay? So what we want to try and do is make it more simple for us to see. All right? Or us to deal with in things that we know. So just to kind of flash ahead, what we'll do is we're going to take our coordinate system, and we've dealt with a coordinate system like this, right? Exactly how you always learned it. We're going to take that coordinate system, and we're going to tilt it. Ray, I see your reaction, like, what? And as I did this more, so it's like I was turning a dial, right? We're going to tilt it so that the x-axis is now parallel to our ramp. So that the surface of the ramp is now our x-axis. Okay? So it would look something like this. Okay? So there now is our axis, where the angle that we tilted it is theta, which is the same angle of our ramp. And if we drew our free body diagram like that, weight is still straight down. The normal force is now perpendicular to the y-axis. Okay? This is parallel to the y-axis? I'm sorry, I said perpendicular. I apologize. Okay? So here's what I contend. We can now put the things of weight, right? The components of weight, because that's what now we have W sub x going like this and W sub y going like that, right? Those are the y components for the x and y components for the weight. We can put these components in terms of this angle here, which we know, which we would know. Does that make sense? Whereas in this case, it's going to take more work than we really want to do to try and figure out what angle the normal force is at. Follow me? Okay? And it ends up being pretty simple. So here's what I'm going to do. I'm going to erase this just because I'm going to end up needing this space, right? But what I'm going to do is I'm going to do a little bit of geometry on you. Woo, geometry. Okay? So here's what we see here. Different triangles. Before we do that, there's W sub x. And I'm just going to, this is exaggerated for a reason. It's not that exaggerated, but it is. And there's W sub y. Do you notice how this makes a right triangle? The weight with these two pieces makes a right triangle? Okay? So I'm going to call then this angle here, which is really 90 minus theta, I'm going to call it phi. Don't worry about what the heck phi is. It's just a label for another angle. Okay? It's a Greek letter. That's all. Usually if we have theta as the first angle, if we need a second angle, you go to phi. Okay. All right. So that's for this triangle. Now I want you to shift your focus a little bit. Shift your point of view. Instead of looking at this triangle, now let's look at this triangle, which is another right triangle. Correct? With the right angle right here. Okay? Well, if this is phi, this is theta. I just want your brains to kind of try and figure that out for a moment. I don't figure it out. Don't ask me why or how. I want you to figure it out.
Is theta, is that the one that includes the little green part?
This right here, from here to here is theta. Yeah, and this little green piece goes into it. Yeah. All right, so this is theta. So let's think about this. This is 90 degrees. So these two together have to equal 90 degrees as well, right? Well, this is 90 degrees. So if that's one piece that equals 90, these two together have to make the 90. So that's why this is theta. Okay? So we've got that. And that's good because we know this angle. Right? So let's take that angle and use it. So here's where I need this other space. I'm going to kind of get away from this. We know, we've already learned that if I take this, the y component, and I add it to the x component, I get the full vector, right? We're good with that? Okay. So w sub x plus w sub y will equal w. Okay? You remember when we deal with vectors, I can draw them in any orientation and order I want as long as I keep the magnitude and the length the same? That's what I'm going to do here. Okay? So I'm going to take this guy, and I'm going to move him. Because, again, I can add them in any order I want, wherever I'd like. So, it's kind of close. There's w sub y, right? There's w sub x. And I added them, and they're perpendicular to each other, right? They have to be perpendicular to each other? Okay. And when I add the two of them together, I get w. Are we okay with this? Shreyas, you good? Okay. All I did was I just took these three, and I just rearranged them and added them together. Really, all I did was take w sub x and draw it down here. That's all I did. Okay? And this angle between them is still theta. Okay? Just like our picture shows. So this allows me to now find out what are the x and y components of the weight, right? Because if I know the y component of the weight, I then know the normal force according to this drawing, right? And if there was friction pushing this way, if I know the x component of the weight, I then know the friction, correct? So it's really important that I know the x and y component of the weight. Okay? So let's look at it. Adjacent, opposite, hypotenuse, right? So let's find w sub x first. The w sub x is the opposite side. What trig function goes with the opposite side? Sine, right? So W sub x is going to be W cosine theta. What? Oops. You told me sine and I wrote cosine. That's opposite of what we've learned already, correct? It's opposite, right? We learned previously that x gets cosine. You put it on a ramp, and because now the angles have changed, it gets sine. How about W sub y? It gets cosine, right? Because it's the adjacent side. Okay? So there's a few different things we can get from this. One, don't take when it comes like situations, they're never complete gospel. It's never complete like this is the answer, right? Because we just changed the situation a little bit and we literally flipped everything. Okay? So it's important that you pay attention to the situation. Okay? Two, this free body diagram tells us why things slide down hills. Right? It's the x component of the weight of the object that is the force that causes an object to slide down the hill. Right? And we can find the acceleration. Let's find the acceleration. Imagine now that this is frictionless. Okay? I got a free body diagram, so I should use
Newton's second law.
Newton's second law, right? It's like if you put on shoes, you better tie them. Okay, and we're just going to look in that x direction. Okay? So if I'm looking in that x direction, I just have W sub x, right? And it's equal to MA, right? Cool. And it's actually negative, right? It's going to be negative. Right? Because we draw the free body diagram I drew up here, right? It just tilted it this way so that this is the positive x and this is the positive y. Right? So going that way, the force being directed that way is negative. Okay? Well, that's then negative mg is equal to g sub x, I should say, right? A sub x. Well, that's actually that. So that's actually m. Ignore my very poor notation. If we look at our tilted coordinate plane, it's pointing in the negative x direction, correct? That's why we give it the negative sign. Okay. Same m's. So the acceleration of an object on a hill, I'm going to make it a little more general, is plus or minus g sine theta. So if you had an object being pushed up the ramp, positive acceleration. Down the ramp, negative acceleration. Make sense? That's why in this case, because the force is negative, it would be a negative acceleration. But if we had a string pulling it up the ramp, then it would be positive acceleration instead. Okay? So what we're going to do tomorrow is a couple things. You're going to set up an Atwood machine on a ramp, right? And you're going to determine what is the angle of the ramp. Make sense? You're going to determine, again, what is the angle of the ramp. Should be pretty simple, pretty quick, okay? And then you'll do a couple other things that have to do with that thing.